This E2M Polytron case study is from one of the world's best-known consumer goods manufacturing companies. Engineers are given a mandate: increase capacity 20 to 25%. Headquarters wants more of their high-demand product shipped out the door. The team is chartered to determine how to eliminate the constraint in the line. If they can, plant engineers believe they have the capacity in the system to increase overall throughput. Do they? Here are the details. Engineers have long suspected the packer as the reason for the line's low throughput. They believe that if they can move the constraint to upstream equipment, they can reach pay dirt. The problem is that their machine has several different subsystems, and there are multiple options to pursue. Before they invest the money in any one of the solutions, they need to verify which one is viable. One method to do that is to pilot the best-known solution on one machine. This will require capital as well as downtime on the line for making the changes, and potential lost production if the solution doesn't work out the way they hope. They call on a team from E2M Polytron to emulate the machine and test changes to see if they work before making them on the physical system. How do you know that the model of a machine represents the machine well enough to accurately predict the outcome of the changes? In this case, the packer had multiple subsystems. Each of these subsystems has a dwell and cycle time for each action, moving a cylinder in and out, for example. Not only did each of these actions have to be modeled, but the timing of them had to be accurate as well. The E2M Polytron team collected data from the machine for each of these subsystems. Code was added so that each machine action could be timed over a period of multiple shifts. This data was then processed, and the result was used for the model. The team then connected the model to the PLC program running the machine. The most accurate way to model the logic of any system is to use the actual code. This is called a PolySim emulation, where the PLC reads the input from the model and directs the outputs to cause actions in the model according to the real logic. Engineers and operations professionals both agreed that the model was spot on. Everyone could move forward with confidence that changing the model would reveal the true outcome. During a brainstorming session, the engineers and the E2M Polytron team created 4 options for a faster infeed: pre-stack the cartons, create a second infeed, lengthen the current infeed, and reconfigure the stacker. A 5th option was to review the business case to replace the entire machine, and the 6th was to do nothing. The team decided to pick the easiest method to model for a faster infeed: reconfigure the stacker. This option, as it turns out, would be the lowest cost and lowest risk to implement. Each of the cycle and dwell times for all the machine's actions were variables in the emulation. The engineers could change any of the timing to determine the impact it would have on the operation of the machine. For example, pushing up a row of cartons could happen quicker. The pusher that moved the stack into the machine could move out and in faster. And the conveyor speed for feeding the cartons in could be increased. With these changes completed, the start button was pressed. The team realized instant success. The rate at which the cartons were entering the machine was up by nearly 30%. Increasing the speed of the stacker had increased the speed of the entire machine. But then things started slowing down. A subsystem in the machine became a constraint internally, and the machine slowed down to its normal design rate. So the team moved its focus to that subsystem and sped it up. Lo and behold, another one became the constraint. This continued until the team resolved that a complete machine rebuild was necessary in order to maintain the 25 to 30% increase in throughput. While disappointed that their best efforts to add speed to the line didn't achieve the desired results, the team was convinced by the veracity of the data that they had the answer. They knew that in order to achieve the results requested, the packer would have to be replaced. They passed that option on for a later time when more funding could be budgeted. Sometimes the best business choices are those not made at all. While the conclusion to do nothing didn't ring with satisfaction, the team avoided purchases that could have easily exceeded $500,000 and potentially caused a huge disruption to their existing operation.